In this lesson, we're looking at vector equations of lines. So essentially, we know an equation of a line requires an initial point and a direction or a gradient, and then relative to some parameter, it will continue to change. So that's no different. When we're looking at a vector equation of a line, it will be defined by an initial position vector A. So if we can think of a point in space A relative to an origin O defined by the position vector A, it will then have a direction D. So from a direction D or at any parallel direction, essentially our vector equation line then is all up to this initial position A, and then that direction vector D over time. So essentially we'll have the vector equation line, which is R parameter T, will be equal to the initial position plus direction multiplied by the parameter T. So this is it. This is our vector equation of a line. Now, for direction vector D, if it needs to be calculated as a point between A and B, then we can say D is equivalent to OB subtract OA, so a displacement vector, or B subtract A. Okay, so now we have the initial information. We'll look at a couple of examples. We should also note as well that that parameter T is an element of a set of real numbers. Okay, so in this first example, we're looking to find the vector equation of a line AB, where points A and B have position vectors OA and OB. Okay, so essentially we need two things, don't we? We need to be able to write the equation RT in that form, A plus TD. So we need to know what A is, and we need to know what D is. So A is nice and simple. A is simply the same vector OA relative to the origin, I plus J take 2K. D will be a displacement vector between B and A. So from A to B, that's our direction. So we're going to look at B subtract A, or OB take OA, and that will be 2, -1, -1, subtract 1, 1, -2. So we end up with 1I, -2J, -1 take -2 is +1, so 1K. Alright, so now we have what we need. We've got A and we've got the direction vector D. So our vector R is going to be I plus J take 2K, and then plus T multiplied by I take 2J plus K. Now if you wanted to, you could also write that in storage vector form. You could say that is T is equal to 1, 1, -2 plus 1, -2, 1 multiplied by T. Or you could say that it's 1 plus T, 1 take 2T, -2 plus 1, or -2 plus T. And that would be a much easier way to deal with those vectors. Okay, so pretty straightforward. That's our vector equation of the line AB. Okay, so now we'll look at a second example. Okay, so in our second equation, we're just looking to find vector equations in the following scenarios. So the first one, the line passing through A12 and B0, -3. So we know this is in 2 dimensions. Again, what we need is the vector A, the initial. So that's going to be I plus 2J. And the direction vector, which is going to be B subtract A. And so B subtract A, 0, -3, subtract 1, 2, 0 take 1 is -I, and -3 take 2 is -5J. So that means our vector equation of the line is going to be I plus 2j and negative I take 5j t. So the first one's nice and simple. The second one, B, we're looking at the line passing through A12 again. So our initial position vector is the same. We've got I plus 2j. And we know it's parallel to 2i plus 3j, so that is giving us a direction vector. The direction vector is 2i plus 3j. So that means our vector equation of the line is going to be I plus 2j plus 2i plus 3j multiplied by that parameter t. Right, when we look at the third one, it's not much more difficult. So we're looking at C here. This time A is a little bit different. We're looking between 3, negative 5, 4, and negative 4, 3, and 10. So the initial position is going to be 3i take 5j plus 4k. And the direction vector is going to be b subtract a again. So we're looking at negative 4, 3, 10. And we're subtracting the initial position 3, negative 5, 4. Means we end up with negative 7 in the I direction, 3 plus 5, so 8 in the J direction, and 6 in the K direction. So that means our vector equation of the line is going to be 3i take 5j plus 4k and add on negative 7i plus 8j 6k multiplied by that parameter t. Alright, that's it. That's the vector equation of the lines. Nice and quick. So we'll quickly look at one extra example. So this will be working backwards. Okay, so the question is asking us to verify that the point P, which is negative 7, 4, negative 14, lies on the line represented by the vector equation R. Okay, in order to do that, to verify that the parameter will be the same for each component when the outcome is equivalent to P. So first step is we're going to put this vector equation in a storage vector form. So we have 5, negative 2, and 4, and we're adding on t multiplied by 2, negative 1, and 3. So that means R can be represented by a single storage vector of 5 plus 2t, negative 2 take t, and 4 plus 3t. Now we want to verify that R can be equivalent to negative 7, 4, negative 14, and the best way to do that looking at solving these three individual equations. So we'll have negative 7 is equal to 5 plus 2t. We will have 4 is equal to negative 2 take t, and we will have negative 14 is equal to 4 plus 3t. Right, if we solve them all and t is equivalent to the same value, that means it is a point on the line. So negative 12 is equal to 2t, divide by 2, and t is equal to negative 6. We add 2 and we get 6 is equal to negative t, so therefore t is equal to negative 6. We subtract 4 and we get negative 18 is equal to 3t. We divide by 3 and we end up with t is equal to negative 6. Now, as time is equal to negative 6 for all three, that means at that point in time it is at the position negative 7 for negative 14. So negative 7 4 and 4 negative 14 lies on the line represented by R. And that's it. That concludes the lessons on the introduction to vector equations of lines.